You know, if I plug in my heater, then I plug in my coffee pot. You know, I'm just always constantly putting them in parallel. And then on our little study guide, it always says what remains constant in a parallel circuit?
Voltage.
Voltage. So now in a parallel circuit, our voltage is always going to remain constant. So if I plug in my heater, this thing's going to get 120 volts AC. If I plug in my coffee pot, this thing's going to get 120 volts AC. And as I keep on adding devices into my, plugging in stuff into my outlet, I'm putting them all into parallel. Okay? So now now in parallel circuits now is that my voltage remains constant throughout the parallel circuits, but my current is divided. So for example, on my heater and my coffee pot, I'm going to have all my current coming in from the power company, coming out to my outlet, then it's going to go into my devices. So I got all my current coming out of my outlet, and then some of it's going to split. Some of it's going to go to my heater, and then some of it's going to go through my coffee pot. And then that current is going to come back up, and those two currents are going to join, and my total current is going to go back into my outlet. So another name for a parallel circuit is a current divider. So a parallel circuit is what we call our current divider. Series circuit is a voltage divider. Parallel circuit is a current divider. What remains constant in a parallel circuit? My voltage. All right. So once we know that, then when we use some of those rules, then we can go ahead and analyze, start analyzing our circuit. So again, the same thing that we want to do. Now you see, I'm going to start talking about straight lining. Remember, I like to have all my components, my power supply on the left-hand side, and all my components on the right-hand side. Okay? So this is already straight lined out for us. We have our power supply on the left-hand side, and then we have our two devices or our components on the right-hand side. Then it says, sketch the electron current path on all schematics. So we're going to go ahead and do that. And my current is going to come out from my negative side of my power supply. It's going to come out, it's going to go through a current meter. It's going to be negative, positive. And then my current, and then when we're analyzing these parallel circuits, this is one time it's okay to talk to yourself while you're doing it. Okay, so talk about it when you're saying it, because I've done it. It really helps out a lot. So all my current is going to come out of my source. All my current is going to go through my current meter. And then when I come up to this first one, I call it current node. And so when I get to my current node, I'm going to branch off my current. So some of my current is going to go up through this current meter, up through this resistor, and then up to this current node. Okay, so I got all my current coming through, all my current's going to go through M1, and then I'm going to come to my first current node, and some of that current's going to split. Some of it's going to go through this branch, what we call this branch. This is a branch. And then the remainder amount of current that's going through from my total current is going to go through my last branch. And so the remainder of that current is going through M3, and then through M4, and then up into R2, and then that current is going to come, and then it's going to go into this current node. And then those two currents are going to combine, and they're going to want to go and seek the positive side of that voltage source. And so all my current is going to go back into my positive side of my source. Okay? So I have all my current, all of my current is always going to be coming out of my source. All my current is going to go through M1. It's going to come through my first current node. Some of my current are going to split. And then some of it's going to go through branch 1. Some of it's going to go through branch 2. Those two currents combine and then go back into my source. So make sure you kind of talk to yourself as you're going through there, because then you know how much current is going through each one of these meters. All right, then what's my next step? So we already straight lined it. We already sketched the electron current path. We indicated all the polarities. We know that all the resistors are plus or minus 5% tolerances. All calculated numbers, 4 digits, rounded correctly, and use the correct metric prefixes and units. So we already completed all our notes. We know we're in good shape there. So now what would be my next step? Fill in everything that we know. So what do we know about the circuit?
11 voltage or 11.
We know our voltage total. Okay, and if we know our voltage total, what do we know about a parallel circuit?
Voltage is constant.
Right, so our voltage remains constant across the parallel circuit, so that means all my voltage is same across R1 and R2. So then write that in right away so you don't forget. Alright, then what's my next step? Well, yeah, so let's first put in our resistance of each one of our resistors. So we know that R1 is what, 1 kilo ohm or 10 kilo ohm? What is that, 1 kilo ohm? 1 kilo ohm. And then R2 is what?
2.2 kilo ohm.
2.2 kilo ohms. Okay? Now what else can we...
The resistance total.
Now we can get our resistance total. How are we going to get our resistance total?
Adding them up.
How do we add them up? In a calculator, what's our formula for RT?
Resistor 1 plus 1.
Is that what it says in the chapter? There's several different formulas that I said in the chapter about how to calculate out total resistance in a parallel circuit.
687.5 ohms.
Okay, but how did you calculate it out?
Oh, 1 divided by resistance 1 plus 1 divided by resistance 2.
1 over.
Good. That's the one I was hoping that you could say. So we got, this is the one that we're going to stick with. So we got, so it's 1 over R1
Plus 1 over R2.
plus 1 over R2, and then we're going to do the inverse of that. And that'll give us our total resistance. Okay? So now, to enter that into our calculator, we have a fancy little key that helps us out for adding these numbers up. Let me bring that up here.
1 over X.
Yeah, this is. So what we have on our calculator, and I think that's the same on the TI-30XA2S, is that we have a key that says 1 over X. This is what we call our inverse key. We're going to use this thing a lot. We're always using our inverse key. So how you want to do that, to add that up then, is that what we're going to do, so everyone find this key on their calculator, whether they have the 2S or the TI-30. Okay, on mine, it's right above the exponent key, the E key. It should say 1 over X. Everyone find their exponent key? Yeah, what did you got, the 2S? I'm going to have a few napkins here.
Well, yeah, it's right on the top of that. 176. Could be X negative 1, by the way.
I think on oh yeah, here's yours right here, right above the E key. Just like mine there, right? Yeah, right above the E key. If you have the 30XS2S, I think it's your X minus 1 key. Try it. Yeah. So on the 32XS, on the 2S, it's going to be the x to the -1 there. That's the same as your exponent. That's the same as me taking 1 over whatever value that we want to do the inverse on. Okay, so everyone find it? Everyone got it then? In good shape? All right. So what we want to do then is how we want to enter this into the calculator. So then we're going to take our 1 kilo ohm. So you're going to make sure you're using your exponent key. If somebody doesn't know how to use their exponent key, let me know. So we're going to put in 1 to the third, and then I'm going to hit my 1 over x key, or my inverse key. Then you should get 0.001. So I just did R1, I did that as 1 kilo ohm. I hit my inverse key and I got 0.01. Then I'm going to add it to R2. So then I'm just going to hit my plus. Then I'm going to put in my 2.2 to the third. And I'm going to hit my inverse key again. Then if I hit equals, I'm going to add those two numbers together. So if I hit equals, and then all I have to do is I have to just do the inverse of that number again. And what do you end up getting on your calculator? What's that?
687.5.
Yeah, so you should got 687.5 ohms. Everyone get that on their calculator? Okay. Okay. Let's do it one more time. Okay. So let's do it with the 30x8 here first. So put in 1 kilo ohm. So 1 to the third. And hit your inverse key. Then you should get 0.001.
I got 1 to the -3rd.
That's the same thing.
Yep, same thing. Yep. I'll put it in my engineering notation too. There you go. So you got 1 to the -3rd. Yep. So that'd be the same thing. 0.001 is the same as 1 to the -3rd. And then I'm going to hit my plus sign. Then I'm going to put in my 2.2 kilo ohms. Then I'm going to hit my, what I call my inverse key. That's what I'm going to call it from now on. Then I should get 454.5 to the -6. Okay. Then I'm going to hit my equal sign. That's going to add them up, and now I should get 1.455 to the -3rd. Everyone get that? Okay. Then if I hit my inverse key one more time,
Okay.
now you should get your 687.5 ohms. All right? That's how you do that. This is going to be our basic formula that we're going to use for parallel circuits. If we just have to remember this one, then that's fine. There's some other ones that we can use if we're using only 2 resistors, but why remember more than what we really need to? There's one other one that we're going to use, but we'll talk about that one later on. But for right now, just remember this one right here. This is the one that we need to know. This one will take care of all our parallel circuits, no matter what the value of our resistors are. So, unlike if this was a series circuit and it had R1 and R2 in series, what would have been our total resistance? 3.2 kilo ohms, right? So our resistance would have increased. What happened when I put them in parallel? What happens to my total resistance? It decreases. My total resistance is going to decrease because if I just had that one resistor, I'd only have, so let's say I didn't have R2 in here, I got all my current coming out of my power supply, then the only current I got going through here then is just the current going through my 1 kilo ohm. I don't have this remaining amount of current going in there. So now when I put that R2 back in there, now I just gave myself a path for more current. So no matter what that resistor value is, I just gave myself another path for current. So now I got more current coming out of my power supply. Some of it, the same amount is still going to go through R1, but then I also have the addition of the current going through R2. So my current starts to go up. As I keep on adding resistance into a parallel circuit, my current is going to start to increase. What happens if I add resistance into a series circuit? What happens if I keep on adding resistance into a series circuit? What happens to my current? It starts to go down because my resistance starts to go up. Okay?
Inversely.
Yeah. This is where we call it, this actually becomes more conductive. Remember I said that we're going to come back to this one. So my circuit becomes more conductive, and that's the representation of my G. So my circuit becomes more conductive as I add more resistance to it. So to figure out your conductance, so the conductance is just equal to 1 over R. So if I wanted to find out what the conductance of the circuit is, I just take my 687.5 and I hit my inverse key. And then I would get 1.455 millisiemens. Okay? So is my conductance directly proportional or inversely proportional to my resistance? If my resistance starts to go down, what happens to my conductance? Goes up. I become more conductive. Every time I add another resistor to a parallel circuit, I become more conductive. Every time I add another resistor, my conductance is going to start to go up. My resistance is going to start to go down, and my inductance or my conductance starts to go up. Because I just gave myself another path for current to flow. So now I still have these two currents. So I still have the current of R1 and R2 coming out of my power supply. Then I add in my third resistor. Now I got more current coming out of my power supply because I just added another resistor. I gave my current a path for another path for my current to flow. So my circuit becomes more conductive. All right. Then we'll come back to that again. So I don't put that on there because we typically are always talking about, when we're working with circuits and stuff, we're always talking about the resistance. What we need to know is that when my resistance goes down, my circuit becomes more conductive. And we talk about that when we talk about a load. Remember, we said that each one of my components here, even though we represent them as a resistor, we call these loads. Okay? So every time I add a load to my circuit, every time I add another load to my circuit becomes more conductive. And as my circuit becomes more conductive, I'm going to get more current because I got more current flow. So as I increase my load, my resistance is going to start to go down. So my load goes up because I'm adding another load. So if I add another load, this really throws people off, this terminology load. If I add another load, if I add the load 3 into it, as I keep on adding it, my load increases, but my resistance starts to drop. I just keep on increasing my load. And as my load increases, so does my current. Okay, so a lot of times we just call these loads, and that's going to be the big terminology. Once you get out there in the industry, you're going to say, well, how much of a load can you put on that? And we'll go over, we'll kind of keep on repeating that terminology load a lot. All right, so now we kind of understand how a parallel circuit works. Let's continue on. Well, here's another thing too. So, because there's going to be a question out here that gets a little bit tricky because there's going to be a missing value in one of our branches. So what is my conductance of branch 1? What's the inverse of my 1 kilo? So what do I get for my conductance for 1 kilo? What is it?
0.001.
1 millisiemens. Okay? And then what's my conductance of R2? 454.5
-6.
million microsiemens. Yeah, microsiemens. There you go. So now, to figure out my total conductance, if I want to find out my total conductance of my circuit, all I have to do is just add them all together. So my total conductance is equal to G1 plus G2. If I add those two together, what do I end up getting? You should get your 1.455 millisiemens. Okay? So my conductance just adds. So I added my conductance just like I do with resistors in series. So conductance in a parallel circuit is just like resistance in series. I just add them together. Okay? So there's going to be a question on one of your packets there, and you're going to have to convert it into conductance to find out what the unknown branch is. Because if I don't know one of these branches, but I do know what my total conductance is, and I know what the other branch is, all I have to do is just subtract that other branch from this, and the remainder is going to have to be going across that. It's going to be the conductance of that other resistor. And then once I figure out what the conductance is, then I just have to hit the inverse of this number again, and that'll bring me back to my resistance. Give me my 1 kilo. All right. Get rid of this for now then. All right, so now we have two items for each item, so now we can go ahead and calculate out the third and the fourth item. So what's my, let's just stick with my total current. So what's my total current going to be? milliamps. So it's just our voltage divided by our resistance, right? Now everyone got 16 milliamps? Agree with that? Okay. Then what's my power total? Alright, 76 milliwatts. Okay. Then what's my current for branch 1? Of milliamps. Okay, and my power for my branch 1?
121 milliwatts.
121 milliwatts. Okay, then my current for branch 2?
5 milliamps.
5 milliamps. And then my power for branch 2?
55 milliwatts.
55 milliwatts. All right. So you can see now our total current was 16 milliamps, right? What's another name for a parallel circuit? Current divider. And so you can see that I took my 16 milliamps and I divided it amongst the two. Directly proportional. The one with the least amount of resistance did what with how much of the current? Majority of it or the least of it? The majority of it. The one with the smallest amount of resistance took the most amount of current. The one with the higher resistance took the least amount of current. If I take those two currents and I add them together, I'll get my total current. Same thing with my power. If I add my power no matter if it's in a series circuit or a parallel circuit, if I add up all the sums of all my powers in my circuit, I'm always going to get my total power. Alright? So now we got to figure out what the meters are. So since we know that this is a current divider, and again we try and talk to ourselves and we say that all my current is going to be coming out of my source, so I'm going to have 16 milliamps of current going down. I'm going to have how much current going through M1 then? 16 milliamps. So then I come to my first current node, and some of my current's going to split off. And how much of it's going to go through M2? 11 milliamps. And then that's going to go up through R1, and then that's going to go into this current node. So how much do I have left then? If I have 16 coming in, 5 of it goes this way, how much do I have going this way? 11 milliamps. So going through M3, I'm going to have 5 milliamps. And then coming up, and I'm going into M4, I'm going to have how much? 5 milliamps, the same as I got the same amount of current going in there. And then I got 5 milliamps going through R2, which we just calculated. And then those two currents are going to combine. And if I had those two currents combined again, how much current do I have going back into my source? 16 milliamps. Okay? So this is our Kirchhoff's current law. The current going into a current node must equal the same going out. So however many currents I got going in, still must equal out the same amount of current that I got going out. That's our Kirchhoff's current law. Okay? Any questions on that? Yeah. So what is R1 and R2 representing? What are those the name that I call those? Loads. Loads. Those are my loads, okay? We're just using those as representations for our loads. Could be light bulbs, could be heaters, could be whatever we want. Those are our loads. As I start increasing my load, what happens to my current? Goes up. Yep, as I add more load, I get more current. Even though I'm adding more resistance to the circuit, my resistance and my conductance actually goes down. Alright. Alright, any questions on it before I wipe it out? Alright, let's take a look at another one here. Well, you know, this, before we get started on our next one here, why don't we take let's just take about a 10-minute break and then we'll